In this video lesson, we're going to be looking at limiting reactants. Our objectives for this video is to define a limiting reactant and an excess reactant, be able to explain the concept of a limiting reactant, and then finally to calculate how much product is produced based on a limiting reactant. Before we actually get into a chemistry example, let's first define what a limiting and excess reactant are and understand the concept behind it. Suppose you get a job at Subway, and at Subway your boss tells you exactly how to make a sandwiches. Notice the ingredients that are on the left. You have bread, turkey, tomatoes, and cheese. Now, as your boss is training you, he tells you exactly how to make a sandwich. To make a sandwich, you need 1 loaf of bread, 3 slices of turkey, 2 tomatoes, and 2 pieces of cheese. Now that you know all the things that are necessary to make a full and complete sandwich, your boss then puts you on the line. Before the customers come in, you notice that you have a certain amount of ingredients. Let's say you have 5 loaves of bread. Let's add in some turkey. Let's add in a couple tomatoes. And let's add in some cheese. All right, look at the following ingredients compared to how much it takes to make one full and complete sandwich. How many sandwiches can you make given the amount of ingredients given to you? Well, let's take a look. Let's first look at the bread. If it was just based on the bread, you would be able to make 5 sandwiches. There's 5 loaves of bread, and you know to make one sandwich, you need 1 loaf of bread. What if it was based on the turkey? Well, let's count. 1, 2, 3, 4, 5, 6, 7, 8 slices of turkey. Remember, to make one full complete sandwich, it takes 3 slices of turkey. So here's one sandwich, here's 2 sandwiches with 2 slices left over. So you can only make 2 sandwiches based on the turkey. What about the tomatoes? Well, it takes 2 tomatoes for each sandwich. So there's 1 sandwich, 2 sandwiches, 3 sandwiches. You can make 3 sandwiches based on the tomatoes. And finally, the cheese. You have 1 sandwich, 2 sandwiches with 1 left over. And so a maximum of 2 sandwiches can be made based on the cheese. Now notice, you can make different amounts of sandwiches based on different ingredients. But if you actually have a customer come in, how many full complete sandwiches are you going to be able to make? Since the maximum amount that we can have is based on the lowest amount, you can only make 2 sandwiches based on the turkey and the cheese. In this case, we would say that the turkey and the cheese are limiting our amount of sandwiches that we can make. They would be known as the limiting reactant. In other words, they're going to run out first before the reaction is going all the way. Your tomatoes and your bread, on the other hand, since you have leftovers, is something we call an excess reactant. An excess reactant is something that you have left over. It doesn't get all used up. Now that we understand the concept behind a limiting and excess reactant, let's look at a few chemistry examples. Let's look at a very common equation. Hydrogen gas and oxygen gas react together to produce water. Notice that the equation is already balanced. Now we've learned that the big numbers in front of every single reactant and product are called coefficients, and these coefficients tell us the mole ratio. In other words, they tell us what perfect ratio that reactants will react together in order to produce a certain amount of product. In this case, notice the 2 in front of H2 and the 1 assumed to be in front of O2. What that means is for every 2 moles of hydrogen gas, you'll need 1 mole of oxygen gas, and the result will be to create 2 moles of water. If these ratios are upheld, that'll mean that there will be the perfect amount and nothing will be left over. Well, let's assume that the pictures drawn below represent moles. So what that means is this H2 molecule will represent 1 mole, and this one will represent another mole, meaning you have 2 moles of hydrogen given. This 1 molecule of oxygen will represent 1 mole of oxygen. Now, since I have 2 moles of hydrogen represented and 1 mole of oxygen, that means that if this reaction were to take place, it should happen perfectly. There shouldn't be any leftovers because the mole ratio is being upheld. Well, let's see if that's the case. Let's rearrange the atoms and see if it creates the perfect amount of waters. Since H2O is 2 hydrogens and 1 oxygen, let's go ahead and create those. There's my 1 oxygen, and 2 hydrogens would rearrange to make 1 water molecule. Let's see if we can do that again. There's another oxygen, and let's see if we can attach 2 hydrogens to it. And we can. Notice that 2 water molecules were made, and that there were no leftovers. In this case, there would be no limiting reactant and no excess reactant, because both were used up equally. Now, in a perfect world, this would happen all the time, and there would never be any leftovers. But we know that's not true. 9 times out of 10, there's always a limiting reactant and there's always an excess reactant. Let's look at the same equation, but a different amount. Notice now I've changed the number of hydrogens and I've changed the number of oxygens. The ratio still remains the same, 2 H2s to 1 O2. But notice the moles represented below. I've drawn in 3 moles of hydrogen and 2 moles of oxygen. Can you guess which one's going to limit the amount of water produced? Your first reaction might be to say the oxygen. After all, you have less moles of oxygen than you do hydrogen. But remember, that's not always the case. The mole ratio tells us what ratio that things will bond together, 2 to 1. So let's rearrange the atoms and see for ourselves which reactant, hydrogen or oxygen, does in fact limit this reaction. All right, let's start pulling over atoms. There's 1 water, there's 2 waters, there's 3 waters, but notice, this last oxygen has nothing else to bond with. It's ready to make a water, but there's no hydrogen available, and therefore you have leftover oxygen. Now, which element ran out first? Was it the H2 or was it the O2? The H2 was what ran out first, and therefore this is known as the limiting reactant. In other words, LR. Since you had leftover oxygen, the oxygen in this case is known to be in excess, and therefore it is the excess reactant, or ER. Let's look at another example. All right, notice the reactants you have on your left side. You have zinc reacting with HCl. All right, let's see how many products we can create based on the given information. We have 2 moles of zinc represented, and we have 3 moles of HCl represented. Let's go ahead and rearrange them and see how much products we can make. Hopefully, it happens out perfectly to where we have nothing left over and nothing in excess. All right, our first product is zinc chloride, ZnCl2. That means I need, for 1 zinc, 2 chlorines. All right, perfect. I've done that. My second product, we can move this out of the way for just a second. There we go. My second product is H2. All right, let's see if we can make that. There's 1H and there's 2H. All right, I was able to make both of my products. Now let's see if I can make more of it. Okay, let's see if I can make another zinc chloride. Well, there's my 1 zinc that I need. There's 1 chlorine, but notice there's not another chlorine to attach, and therefore that product does not fully make. Well, what about the hydrogen? Well, there's 1 hydrogen. Let's add another hydrogen. But notice there's also no hydrogens as well. Because there's not enough to make products a second time around, these reactants are known to be in limbo, or just sitting there. What was the limiting reactant, and what was the excess reactant? Well, you did have enough zinc to make a second product, but it was the chlorine that ran out. Which reactant contains the chlorine? The second one right here, the HCl. Because the HCl was what ran out, this is the limiting reactant. The zinc, on the other hand, was excess. You had leftover enough to make another product. Now that we get the concept of a limiting reactant and an excess reactant, let's take a look at a stoichiometry problem. Consider the following problem that's stated below. It gives you the reaction of Na plus Cl2 yields NaCl. The situation is this. If you have 30 grams of sodium and 56 grams of chlorine, how many grams of NaCl can be produced, and how many grams would be left over of the excess reactant? This situation is different from what we've seen before because it's giving us two values for our reactants. It's telling us we have 30 grams of sodium, and it's telling us we have 56 grams of chlorine. What that means is one of those reactants will run out completely, meaning all of it will be used up. That will be the limiting reactant. The other reactant will have leftovers. It won't be all used up, and that will be our excess reactant. In order to figure that out, we need to go through some steps. Here's what we do. Let's go ahead and start out with what we're given. We have our equation, Na plus Cl2 yields NaCl. Before we can even do anything, we have to make sure that's balanced. Take a moment and balance that equation. You should have gotten 2, 1, and 2 for your coefficients. Now that we have that, let's go ahead and go through with the math. I'm going to turn to another screen now so that way we have some space. Feel free to go back in the video if you need to see the information. All right, remember we were given 30 grams of sodium and 56 grams of chlorine. Now up in the corner, I'm going to write my equation so I don't forget it. All right, my first step is I want to take my given amounts, which is 30 grams of sodium and 56 grams of chlorine, and I want to convert that into moles. Since we're in grams, we're going to have to divide by a molar mass. Sodium is approximately 23, and chlorine, remember you have 2, is 70.9. By dividing those two numbers, it's going to give me my number of moles. 30 divided by 23 gives me approximately 1.3 moles of Na. 56 divided by 70.9 gives me approximately 0.79 moles of chlorine. Now what I need to do is I need to say, based on these values, what is the maximum amount of NaCl that can be created? In other words, I'm going to have to use a mole ratio. Let's do the top one. I want to get sodium converted to NaCl. Sodium goes on the bottom, and NaCl goes on top. The coefficient in front of sodium is 2, and the coefficient in front of NaCl is 2. Therefore, the number of moles I can produce of NaCl using sodium is 1.3 moles. Let's do the same thing instead for chlorine. Chlorine, I have 0.79 moles. If I were to use all of the chlorine, let's go ahead and see how many moles of NaCl I could create there. NaCl's coefficient is still 2, but chlorine's coefficient was 1. If I take 0.79 times 2, I get approximately 1.6. Now, notice what I've done. Look at the top conversions using the sodium. If I were to use all 30 grams of sodium, what that means is going through all my calculations, I can create 1.3 moles of NaCl, my product. If I were to use all of my chlorine, I would be able to create 1.6 moles of my product NaCl. Since I can only create 1.3 moles of NaCl using the sodium because it's the lower amount, this is the amount that's actually created. And sodium, therefore, is my limiting reactant because it makes the least amount. And therefore, I'm going to use the 1.3 moles, not the 1.6, when I'm doing my final third step. Remember, my question wanted to know how many grams of NaCl. Well, I just figured out I can produce 1.3 moles of NaCl, so I need to now convert that into grams for my final step. Going from moles to grams is multiplying, and the molar mass for NaCl is 58.44. By taking 58.44 and multiplying that by my number of moles, which is 1.3, I calculate approximately 75.9 grams of NaCl. Now, that's the first question, But going back, remember, the second question asks how many grams of the would be left over of the excess reactant. Well, we figured out that sodium was the limiting reactant, and therefore chlorine must be the excess reactant, or ER. All right, let's go ahead and solve that. How much would be left over? I'm going to start with this value right here. I know 1.3 moles of NaCl can actually be created. Now, the reason I'm starting with 1.3 moles of NaCl instead of the answer we got in grams is because I'm eventually going to have to convert back to moles anyway. So it makes sense that I start with moles and save myself some trouble. All right, we calculated that we can produce 1.3 moles of NaCl. That is the maximum amount with sodium being our limiting reactant. So let's figure out using a mole ratio how many moles of chlorine it takes in order to do that. NaCl goes on the bottom because that's what I'm currently in here, and Cl2 goes on top because I want to know how many moles it takes to create the 1.3 of my product. NaCl's coefficient was 2, chlorine's was 1, so by taking 1.3 divided by 2, that gives me my number of moles of chlorine. In this case, it's 0.65. Now, what does this value mean, 0.65 moles? What that means is to create my amount of product, which was the 1.3 moles, it takes 0.65 moles of chlorine in order to do that. Now remember, we figured out at the very beginning that my total amount of chlorine given at the very beginning was 0.79. However, out of that 0.79 moles of chlorine originally given to me, I only needed to use 0.65 moles of chlorine to create my product because the reaction stopped after that amount was used. Therefore, how are we going to figure out how much is left over? We do that by subtracting. If we subtract my original amount and my amount that is used, I get the amount that's left over. And in this case, it's 0.14. That means 0.14 moles of chlorine was left or not used in the reaction. Now, the answer was not asking how many moles of chlorine, but how many grams. And therefore, my final step is to multiply this by the molar mass of Cl2, which is 70.9. By taking 70.9 and multiplying that molar mass by the amount of moles not used in the reaction or left over, I get my final answer, which is approximately 9.93 grams of Cl2. That is the amount that is left over after the reaction is complete or unused. This concludes the video lesson for limiting reactants.